Hello everyone. For today's video tutorial, let's talk about these logic gates and logic circuit, which is part of our IGCSE Computer Science syllabus. This is chapter 3. So the objective for today's tutorial is let's talk about what are the different types of logic gates we have in here, what is a logic gate, and as well as we will try to prove this type of circuitry about relating to how the device can turn on and turn off, or can value zeros and ones. So by default, or by definition, as we know about logic gates, so this is just a device that acts as the building blocks of digital circuit. So in short, oftentimes these are referred as the transistors built in our processors. So our CPUs are made up of several tiny transistors that can turn on and off at the same time, as our computer is just limited to two things: understanding the ones and zeros, or would say the yes or no for that one, on and off. So these are the 6 logic gates that we have to discuss this time, proving them on how they functions. The NOT gate, the AND gate, the OR gate, the NAND gate, or we call it a NOT AND gate, the NOR gate, which is the opposite of an OR gate, means not or NOR gate, and then the XOR, or we call that one as the exclusive OR gate. So let's discuss these things for today, as well as to prove them when there's an input's gonna be here, and what will be the output out of that. It's gonna be coming in this direction. So in this example of this NOT gate, so if you observe right now, there is one input and expected to have one output, while this AND gate and the rest of them in the illustrations, you can see that there are 2 lines here, means there are 2 possible input you can have and 1 output you will get. So they can be combined depending on the conditions of your statement later on, and the combinations of them can be labeled in the truth table, where you have to combine those gates and see what will be the possible output if you will have them there. So these are just example of the table that you can have. So example, there are, in this particular situations, there are 2 output. There's 2 input here, sorry. So there's 2 input you will have. So the decision making, what it will be, the same thing in here, there will be 3 inputs as well as the 4 inputs. So instead of going through the drawing, I will just offer you this website. This is a very good website for that, where we can construct our logic gates and see what will be the possible output. So just in this particular situations, the truth table we have here, there is like 2 inputs, so you can make use of this toggle switch. All right, this is the thing. So this is what we have, the 2 inputs at this moment. So where 2 is 0 right now, 0 1, where you can turn on one of it, another condition is turn on the other one, and the other one is both are on, so like this way. So and then you can add another input here if you'd like to, that makes it into this particular condition. So these are just different combinations of inputs you can have in these situations. And the last one, we have the 4 inputs. There are more of it, but observing the past papers, they are limiting to 3 inputs so far. This is what I known in the past papers when I solved. So here's the thing. So these are all on, means all of this one here. So different combinations you can have it here. So let's make use of it to prove our logic gates. So let's focus first on our first gate here. Let me just minimize this so that we can have them in side by side. So the first one we have on your screen, you can see right now, it's about the NOT gate. So the truth table of NOT gate, if you look at the descriptions of it, the output of this particular situation is the opposite of the input. So this is called the NOT gate. So if you observe here, it says if you input 0, the result is 1. When you input 1, the result is 0. So I will prove it using this particular website. So you will have one input. We'll put one input for the NOT gate, and then you will have to put this NOT gate drawing, this one here. So this is the thing here. Put it in here, this side, as well as what you will do to show it, put a light bulb into it and connect them. So if you connect them, let me just make it smaller, connect the gate, and then there you go. So see, it proved that if 0, the light will turn on when, or the decision is on, but when it is on here, it will turn off. So this is the thing here. This is about the purpose of the NOT gate. So I think that's easy to know. It's just the opposite. Now let's move to the next one. The next one is about the AND gate. So the AND gate is represented by this circuit, this logo, or this picture. So this is the truth table for that. If you will have this conditions, if you observe right now, there is only one way that this particular data will turn on. It's only when the two switch or the two circuitry will be on at this moment. So let's prove it using this particular thing here. So let's input two data here. All right, this is the two data we have here, where we can add another this AND gate. We'll put it here in the middle, and then of course to show it, there should be a light bulb into it. So let's connect the inputs to the AND gate. There you go. So connecting them, as the decision says, when both are off, nothing will happen. When one is on, nothing will happen. When one is on, nothing is happening. But you turn on both, the light will turn on. So that is the purpose of an AND gate. So both switch must be turned on before the decisions will be yes or an on. So we have NOT and NAND and NOT gate and the AND gate so far. Now let's move to the third one. It is the OR gate. So the OR gate have a different method. It says here, as long as one of it is on, the output will be on. So let's do it using the illustration again. Let's input 2 here, to switch here, with an OR in the middle of it instead of an and we'll put the light bulb as well. So I will save space a little bit so that I can have more space for the rest. So let's connect both of it to the gate, and there you go. So when both are off, nothing happens, but any of it will be turned on. Look at that, it's turning on, it's turning on, as well as you turn on both, it will turn on. So that is the purpose of the OR gate. Let's move this a little bit closer so that we have more space for the rest. There you go. All right. Now let's move to the NAND gate. So the NAND gate is represented by this logo. If you observe, it is just a combination of an and the circle in front of it, which is the NOT. So basically it is just the opposite of an AND. So if you observe the AND we have, if both are on, it will be turning on. But if the NAND gate is used, if both are on, it will turn off, and if nothing is, one is on or nothing is on, it will turn on. So this is the thing here. So again, this is just the opposite of the AND gate. So let's do it. Let's prove it with this particular illustration. So let's put it next to the AND as well. It's gonna be here, and let's put the NOT AND here, the NAND. All right, so if you observe the drawing, there's a little circle in front of it, and let's put this light bulb also to prove it. Again, when the blue is open, means it's active, means it's on. So right now both are off, it's on. One is on, it's on. One is on, but if you turn on both, it turns off. So that is the NAND gate. So it's the opposite of an OR gate only. And then we will have the NOR gate. So the same concept, it is the opposite of the OR gate. So the OR gate, the 3 is if the 3, any of the input is 1, so all of this will turn on. But this time it's the opposite. Any turn on, it will turn off. Any of this one is off, both of are off, so it will turn on. So let's take a look at the input again. Let's prove it here instead of drawing it and then putting our gate, which is the NOR gate. Alright, so let's do it here. Let's make it like this, and then let's put the light bulb here. So connect them all. There you go. So if both are off, it will turn on, but if one is on, nothing happens. One is on, nothing happens. If you both turn it on, nothing happens. So that's the thing. So both must be turned off for that. While this one, as to repeat, the AND is different. Only it will turn off when both are on, like that way. So we have now 1, 2, 3, 4, 5 gates. So let's talk about the last gate that has been discussed here. It's about the XOR. Actually, XOR represented by exclusive OR. So an exclusive OR gate is technically designed to turn on or to give an input of on or yes or 1 only if one of the circuit or one of the input is actually on. So 2, if both are on, it should not work because it's already an AND. If both are off, it will not work. But if one of it is on, this is the thing will happen. So this is about exclusive OR. So let's take a look at the example illustrations here. There you go. Now I have the 2 input here, and we will simply put that exclusive OR. There's an exclusive NOR, but I haven't seen this in the past papers, so let's just leave it. Let's just focus with this one here. So connect them both. This is the exclusive OR, and let's put the light bulb here. Connect them. There you go. So both are off, nothing happens. Turn it, one is on, works. The other one is on, it works. Both are on, it's nothing, it will not work. So that's the thing. Those are the gates we have in here. So I hope you have learned something out of it visually, how these gates actually works, the decision making of computer. This is just the transistors that built into it through to you know, the 2 transistors and on and off. As we know, computer only understand binary digits, zeros and ones. So just like imagine this is 0 and this is 1 right now. This is 0, this is 1. Both 0, both 1, like that. So the decision making of transistors will only be that particular thing. So again, our computers, our processors are made up so much, too many tiny transistors to make decision making out of it. Alright, so that's the whole video for today, and next video I will try to explain to you this particular activity. Let's zoom out, like this activity on how this particular how we can prove this particular statement that they represent the same logic gate. So let's just have this on the next video. Alright, bye for today.